Hello, everyone. So the first talk of this session will be about importance sampling for robust and efficient multi-level Monte Carlo estimator for stochastic reaction networks. This is a joint work with Dr. Nadeeb Rashid and Professor Raul Tamponi. So my talk will be structured as follows. So first, I will introduce the needed concepts for the understanding of our approach. Then I will explain the main details related to how to design importance sampling for a robust and efficient multi-level estimator. Then I will showcase the advantages of our approach through some numerical experiments. And finally, I will conclude. So as some of you may know, deterministic models describe an average or mean field behavior, and it's only valid for systems with large populations. And there was a considerable experimental evidence showing that systems with small population count have dynamics dominated by stochastic effects. This led to the fact that discrete state space and stochastic simulation approach became more and more relevant than continuous state space and deterministic ones. And this implied the elaboration of the so-called theory of stochastic reaction networks. So the framework of stochastic reaction networks has many applications. For instance, the study of the evolution of biological models, chemical reactions, the spread of epidemic processes, and virus kinetics. For instance, this kind of framework can be very relevant to study the evolution in time and space of the spread of coronavirus. So formally, what is stochastic reaction network? It is a continuous time Markov chain that we denote here by the state vector x, where the component of the state vector can be seen as a counting number of each agent or species in the system. And the interaction between these species is described through G-reaction channels that are characterized by the pairs nu-J and aj, where nu-J here denotes the stoichiometric or state change vector, and aj represents the propensity or jump intensity function. In this setting, the propensity functions satisfy an important relation, which is relation 1, which states that the probability to observe a change in the state in the time interval t plus delta t, due to the firing of the G3 reaction, is proportional to the length of the time interval, which is delta t, with a constant of proportionality equal to aj. This relation is important for the derivation of the chemical master equation for these systems, and also to derive other properties for stochastic reaction networks. For instance, it's used to derive the Kurtz random time change representation, which is the basis of most of the schemes derived to simulate stochastic reaction networks. And here, this representation says that the state vector is solution of a nonlinear system of stochastic differential equations that are driven by Poisson random measures. So some of the typical computational tasks that one can be interested in to solve in the context of stochastic reaction networks are the following. For instance, one can be interested on the estimation of the expected value of a given observable of the state vector at capital time t. And as an application, one can compute the expected counting number of the ith species in the system, where here the observable is the projection. Moreover, one can be interested on estimating hitting times of the state vector. And as an application, one can be interested on computing the time of the sudden extension of one of the species in the system. So to perform these and other similar tasks, one needs to design efficient Monte Carlo methods and also to sample efficiently paths for stochastic reaction networks. So there are mainly two classes of simulation methods for stochastic reaction networks. The first class is what is called Pathwise exact method, which reproduces exactly the statistical distribution of stochastic reaction network process. For instance, we name the stochastic simulation algorithm and the modified next reaction algorithm. However, these kind of methods are penalized with a huge computationally cost. To overcome this undesirable feature, pathwise approximate methods were proposed in the literature, and the most popular one is the explicit Tau-leap. And also there are some implicit schemes that are relevant for systems characterized by having simultaneously fast and slow time scales, such the one that we propose in a different work that we call split-step implicit Tau-leap. So in this work, we focus on the scheme, on the explicit Taulib scheme, which is basically obtained through the Kurtz random time change representation. And the updating step of the explicit scheme is obtained by taking a forward Euler approximation of the integral arising on the internal clock of the unit rate Poisson processes. So let's remind of the Monte Carlo method here. So let's say that we have a setting where X is stochastic process and we have certain observable that is giving the measurement of interest. And let's say that our aim is to approximate the expectation of g of x at capital time t using some sort of approximate path of the true process. Then the idea of the Monte Carlo estimator is to evaluate, is to approximate the expectation using some average of the observable evaluated at independent realizations of the paths generated with the approximate algorithm. And one can show that if the approximate algorithm has a weak error of order delta t, then to control the error with a certain pre-selected tolerance tall, then the Monte Carlo complexity can be of order tall to the power -3. In this view came the multi-level Monte Carlo method, which first was introduced by Kebaier with the 2-level version, and then generalized and popularized by the work of Giles, with the aim of improving the Monte Carlo complexity when estimating expectations. In this method, the setting is the following. So we consider a hierarchy of nested meshes that we index by level L. We also consider a geometric sequence of the time step sizes with an argument k that is taken to be equal to 2 in most of our numerical experiments. And we denote by zeta L the approximate process generating using step size of delta TL. So the idea of the multi-level Monte Carlo estimator is to express the expectation of interest as a telescopic sum, which involves two main contributions. The first contribution is an expectation at the coarsest level, which is estimated through a single level Monte Carlo. And the second contribution is a summation over the levels of expectations of the observable, of the difference of the observable evaluated at the coupled level zeta L and zeta L minus 1. These expectations are estimated through the coupled version of the Monte Carlo estimator, where the coupled levels here, zeta L and zeta L minus 1, are simulated with the same randomness, but with different time resolution. I should emphasize that the key idea when constructing the multi-level estimator is to come up with a coupling that ensures that we have a decreasing sequence of the variance of the coupling terms with respect to the level, which means that we have a decreasing sequence of the needed number of samples per level, which means that we sample less and less for levels that are more and more costly. Moreover, it was shown that the multi-level complexity fulfills relation 4, where we see here that we have different scenarios of the complexity depending on the relation between 3 parameters alpha, beta, and gamma, where alpha here is related to the weak convergence, where alpha here is related to the weak error convergence, beta is related to the strong convergence, to the strong error convergence, and gamma is related to the work rate. Moreover, one can see that one can obtain the optimal complexity of the multi-level estimator, which is told to the power -2, in the case where we have the strong convergence rate beta is strictly greater than the work rate gamma. As I said earlier, the main challenge when constructing the multi-level estimator is to come up with a good coupling. And the coupling idea in the context of stochastic reaction networks is based on the simple idea on how to couple two Poisson random variables. As an illustration, let's say that we want to couple two Poisson random variables, P1 and P2, with the corresponding rates lambda 1 and lambda 2. Then the idea is to decompose these two Poisson random variables as a sum of a common Poisson random variables with a rate equal to the minimum between the two rates plus some correction terms involving independent Poisson random variables. And one can show that if one computes the variance of the difference between these two Poisson random variables, we will obtain we will obtain that it's equal to the absolute value of the difference between the two rates, which is much less, smaller than the case when P1 and P2 are independent, and in that case, the variance is equal to the sum of the rates. So now let's give the main details of the pathwise importance sampling that we propose for the robust and efficient multi-level estimator. And first, let's motivate why we need importance sampling. So it was observed that when constructing the multi-level estimator for pure jump processes, one can observe what we call catastrophic coupling, which is represented by relation 5, and it can be explained as follows. So let's say that we have a random variable YL to be equal to the difference between the coupled Taulip approximations x bar L and x bar L minus 1 at capital time T. Then when constructing the estimator, one can observe that the proportion of YL to be different from 0 becomes more and more tiny as we go deep in levels. This undesirable feature may have bad consequences. For instance, the large kurtosis problem, as was pointed out by the work of Moraes, Tamponi, and Villanova. And this may lead to an expensive cost to get a reliable and robust estimate for sample statistics in the multi-level setting. Now, why large kurtosis is bad can be seen through the expression of the standard deviation of the sample variance of the random variable YL, where we see here that in order to have accurate estimates of the variance of the random variable YL, one needs to control the standard deviation, which means that we need a number of samples that is much larger than the kurtosis. So if the kurtosis is large, this induces an expensive cost to get reliable estimates of the sample variance. Now, why we need accurate estimates of the sample variance can be seen through the expression of the optimum number of samples, where we see here that it's expressed through the sample variance at levels L. So the goal of our work here is to design a pathwise dependent importance sampling in order to improve the robustness and the complexity of the multi-level estimator. So let's illustrate what we call the catastrophic coupling through a simple example. So let's say that we have an example where we have an observable that takes values only either 0 or 1. And we denote by GL its numerical approximation at level L in the multi-level estimator. Then if we express YL as the difference between GL and GL minus 1, then we can see that it can only obtain values of 1, minus 1, and 0 with the corresponding probabilities. And we can show that if the probabilities that YL gets values different from 0 goes to 0 as we go deep in levels, then we can show that the probability of YL equal to 0 converges to 1 as we go deep in levels. And also we can compute an approximation of the kurtosis and shows that it's equal to the inverse of PL plus QL, which goes to infinity as the levels gets larger. So we can see that to have accurate sample variance estimates of the sample variance, one needs to control the standard deviation of the random variable YL, which implies that we have a number of samples that should be greater than the kurtosis, which we have shown that it goes to infinity as we go deep in levels, and which imply an expensive computation cost. So to explain our importance sampling idea, we need first to illustrate the standard path coupling in the context of stochastic reaction networks. And we do it here for one species and one reaction channel. So let's say that we have x bar L minus 1 and x bar L as two explicit Taulip approximations of the true process based on two levels L minus 1 and L. So the idea of coupling in the context of stochastic reaction networks is to express the updating step of the difference between the coupled paths from time Tn to time Tn plus 1 as contributions coming from sampled Poisson random variables and the different coupling interval Tn, Tn plus delta TL, and Tn plus delta TL, Tn plus 1. where the rates of the sampled Poisson random variables here involves the difference between the propensities evaluated at the coupled levels n times Tn and Tn plus delta TL. So the idea that we propose for the pathwise importance sampling is to replace the original rates that arise in the standard path coupling by new rates that we parameterize by lambda JLN, where this parameter lambda is determined such that our change of measure decreases the kurtosis of the multi-level estimator at the deep levels and also improves the strong convergence rate. Moreover, our change of measure is done few times across each simulated path and is only applied when we fulfill these three conditions. So the first condition basically says that we apply change of measure only for reaction channels whose stoichiometric vector induce a change in the observable. The second condition is meant to prevent the likelihood from being equal to 0. And the last condition is the main motivation of our work, where we want to do the change of measure whenever the difference of the observable at time Tn is equal to 0. So our analysis suggests that a suboptimal choice of the parameters lambda are equal to a proportional quantity to the original rates, but where the constant of proportionality is a scaled constant with respect to delta TL, and basically it's equal to delta TL to the power minus delta, where delta is a scale parameter now in importance sampling, and it lies between 0 and 1. So table 1 shows the main results that we obtained for our approach compared to the multi-level, to the standard case, which is multi-level Monte Carlo without importance sampling. In fact, our theoretical estimates and numerical experiments show the following. So first, we reduces the growth of the kurtosis from delta TL to the power minus 1 in the standard case to delta TL to the power delta minus 1 in our approach. Moreover, we improved the strong convergence rate to go from 1 in the standard case to 1 plus delta in our approach. This led to improvement of the complexity, where we obtained, thanks to our approach, a complexity, the optimal complexity, which is of order 12 to the power minus 2. And finally, all these improvements are obtained with negligible additional cost. In fact, we show that that the average cost of simulating coupled paths at level L has similar expression for both approach, the standard one and our approach. So now let's showcase the advantages obtained through our approach compared to the standard one. And for this aim, we consider here one of the examples that we tested in our work, which is the Michaelis-Menten enzyme kinetics problem, and which consists of 3 reactions and 4 species. The aim of this example is to approximate the expectation of the counting number of the third species at capital time T, where the third species here is the catalyst C. So through this table, we show a comparison of the convergence results between the multi-level without importance sampling, multi-level Monte Carlo without importance sampling, and our approach, where we combine the multi-level estimator with importance sampling for different settings of the scale parameter delta. So the first observation is that thanks to our approach, we decrease the kurtosis at the deepest level in the multi-level estimator from a value of thousands to a value around 6, where we consider delta equal to 3/4. Moreover, we observe consistently that we obtain a strong convergence rate that is equal to 1 plus delta compared to 1 for the case of multi-level without importance sampling. And this led to improving the complexity of the multi-level estimator to achieve the optimal 1, which is 12 to the power minus 2. So to validate our claim about the cost, here we show 2 plots. The first one, we compare the average cost per sample path per level for the 2 approach, the one without importance sampling and the one with importance sampling. And as you may see here, we have approximately the same cost for all levels. Moreover, in the second plot, we show the average number of steps where we apply the change of measure through the blue dots. And as you may observe here, it's a bounded quantity with respect to the number of time steps in the multi-level estimator, which means that we apply our change of measure a few times across each simulated path. So through this plot also, we want to show the effect of our method on the kurtosis and the strong convergence rate. And let's start by the top right plot, where we see here the behavior of the variance with respect to the level. And we see that we have a strong convergence rate of order 1. Moreover, if we see the bottom right plot, we see that the kurtosis deteriorates as we go deep in levels. This is for the case where we do not do importance sampling in the multi-level estimator. Now, if we apply our approach, then we see that we improved the behavior of the decay of the variance, where here we get a strong convergence rate that is equal to 1 plus delta, where delta here is equal to 3/4. Moreover, we see that we improved the rate of growth of the kurtosis, and we obtain a value around 6 for the deepest level, which is much less than the case without importance sampling, as you may see here. Okay. So finally, through this plot, we want to compare our approach, which is represented, the numerical complexity of our approach, which is represented by the green dots, compared to the standard multi-level estimator, which is represented by the red dots, and the Monte Carlo estimator with an exact method, in this case, the SSA, the SSA through the blue dots. So the first observation is that our method achieves a numerical complexity of order tau -2, which is much better than the standard approach, which is tau -2 log tau square. Moreover, we achieve the same complexity as the exact method, as the Monte Carlo with exact method, but with a much significantly smaller constant. So now let's conclude. So through our work, we designed a novel method that combines a pathwise dependent importance sampling with a multi-level estimator to obtain a robust and efficient estimation of statistical quantities for stochastic reaction networks. So our method decreases dramatically the high kurtosis observed at the deep levels of standard multi-level estimator when it is due to catastrophic coupling. Moreover, our theoretical estimates and numerical experiments show that we improve the strong convergence rate from beta equal to 1 to beta equal to 1 plus delta, and this improvement comes with negligible additional cost. This results in an improvement of the complexity to achieve the optimal complexity, which is tau to the power -2. And I should emphasize that we obtain this improvement without the need to simulate steps with an exact scheme, as was done in previous work in this setting. And more details can be found in our work, which was recently accepted in the Statistics and Computing Journal. Now, as a future work, one direction is to design a more optimal importance sampling scheme, for instance, by considering a hierarchy of the scaling parameter delta with respect to the levels. In fact, we observed that for the asymptotic regime, for large values of the levels, we need values, for a good performance, we need values of delta that are close to 1. However, this may impact badly the pre-asymptotic regime corresponding to a small, value of the levels. A second direction can be to design a novel importance sampling scheme to address another issue that can lead to this high kurtosis problem, which is catastrophic decoupling issue. And finally, we can try to generalize our importance sampling approach to diffusion problems. In fact, there was observed that some pricing problems where we have low regular payoffs, one can observe this high kurtosis issue as well. So a good strategy of importance sampling to be coupled with multi-level estimator can be a very relevant alternative. So these are the references that I considered in this talk. And thank you for your attention.